Yeah, this is the second of two rooms.
Okay.
So yes, you can come up here. I don't think you'll need the, well, you can use the spectroscope. We haven't used the spectroscope for this one. Okay, so I have, well, essentially a beaker. What I'm going to be doing is pouring a liquid into one and the other. Okay, so ask me some questions.
Can I borrow this chair?
No.
Oh, sorry. That's a question.
What's in the bottle?
Okay, what's in the bottle? In addition to air, it is what it says it is.
Tonic
Tonic
water. Okay.
contains what? Atomic water. Yes, it is. Show me something that isn't atomic. Dang. Yeah, remember chemistry?
The vacuum of space.
The vacuum is, well, actually there is mostly space. Okay. But it contains quinine is what it says.
Quinine.
Which is, yeah, this kind of complicated molecule. It sort of goes on and on. So what happens? Well, it contains a little bit of carbon dioxide too. That smells like it. Okay, this is a couple years old.
Oh.
But still, you don't have to drink it. Don't drink the reagents. Okay. So let's see. Oh, I know. This thing has to warm up. And it does get kind of warm. Okay, keep asking me questions.
What is that?
It
What are-
says
It says black ray in the back.
black ray. Okay.
Long wave ultraviolet lamp, it also says.
Oh. Okay.
Okay. Any
This
questions?
is facing right towards me.
What
so.
does that do?
It tells you what it is. What do you think it does?
Light.
It shoots ultraviolet rays right out of the sky, right?
Absolutely.
Let's see. Do I have the right thing hooked in? Goes here. Dang, physics. I actually have to deal with the real world here. Okay. Now, I'm going to point this, not at you, but I'm going to point it away,
Okay.
because point it away from everybody.
How long will it take for us to get a sunburn if we stood in front of that?
I don't know, how long do you want to stand there? Probably a very long
It
time.
would take me a really short time.
Yeah, probably me too.
Be
Okay.
like a minute in front
How long
of the
will
thing
you
and
see
it
here?
burned.
Actually burned.
Okay, so what do you think I'm going to do?
Science.
How? What am I going to do?
You're gonna measure some tonic water in a beaker.
Okay, at the water?
Through the water.
Through the tonic water. Okay, so it's going to have something to do with that. What do you think is going to happen?
I think it's going to glow.
Okay.
Something's gonna glow.
Why? Why would it glow? Because we're talking about light?
Well, if we knew that answer, we wouldn't be the students.
Okay, but you have to guess.
Fair
You know,
enough.
you have to ask questions about, okay, so glowing, what is glowing? No, I mean, what does it mean? What does it mean to glow?
It's emitting light.
It's emitting light. What is emitting light? First of all, this would be, right?
The lamp is putting energy into the tonic water, which is then releasing that energy back out as light. Because
Okay.
it's exciting the electrons up and down, and when they go back down, they emit light.
Okay, up and down, so are they jumping up and down? No, they're jumping up and down
In the shells.
Wait.
within the shells, yeah. So from one shell to the next, according to specific frequencies that it absorbs. Now, this is actually a broadband ultraviolet light. So high energy or lower energy compared to visible light?
All right.
Hi.
High. So higher energy, it's meaning it's at the short wavelength or high frequency. Higher frequency, just higher frequency than the violet that we had over here. Okay, I think this is, oh, yeah, you can see a little bit. Whoa.
Okay.
Yeah, okay, so that's doing something. So what is happening? This is, well, it's doing a little bit with that. Let's see. Okay, it does it more with some things than with others. Do that with my shirt. Whoa, it shows my dandruff. Yeah, you can laugh. You don't have the dandruff.
Sorry.
See, well, it doesn't glow too much, but this seems to respond. So my lab coat's getting excited. The electrons in my lab coat are getting excited. I just like to use this as, actually there were a number of people in the department who've never seen this. This is something I discovered in the fraternity when we were making,
Oh, yeah, the tonic
it is back when we had black lights, 4-foot black light. And we were drinking something and tonic.
Something, I wonder
We were
what.
pouring this into the black light, and suddenly we saw this stuff doing what it did. Okay, so what do you see here now?
Tonic
Tonic
water.
water? Okay, you're trusting it's tonic water, which it is.
How much tonic water?
How much are you pouring in?
It says, well, it's about 160 milliliters.
About?
Okay.
What size beaker is that? 300?
This goes up here. It says 300.
Okay, so
Okay, so
300
this is
milliliter.
this is actually a 400 milliliter beaker graduated to 300. So that's what size this is. And this is called an Erlenmeyer flask. It goes up to 250 milliliters at this point. What this does is it lets you, it's shaped like this so you can swirl stuff around in it. So the only purpose of that is to get a nice, let's see, get a nice show. Okay, let's see, does this turn around? Okay, now. There. See that a little better. Okay, so that's actually, it's kind of interesting to see something that, a liquid that actually glows under here. Let's see, let's put it up a little. Oh, sorry, you guys are, I'm pointing it directly at you. No sunburns intended. Let me do it this way.
Okay.
The fume hood's kind of a problem.
Can you see there anyway? That's where my power supply is. Okay, unfortunately.
Oh, now the lamp's in the way. Okay.
Love being directed. That's really cool.
Oh, that's cool.
Okay, so this is why I use an Erlenmeyer flask. So you can swirl it around. So let's see what happens here.
This thing makes any
Okay, when I pour that in there, is that ultraviolet? Does it look ultraviolet? No, because, well, first of all, because we can actually see it and it's brighter than what we're seeing here. Now, why is it, if we put in a very high frequency of light, we can see it here? That's the big question now.
Because it doesn't have to emit the same amount of energy back out, so it can release a lower frequency photon back out.
Exactly. So what we're doing is we're putting a very high energy photons in there, okay? So it's like too much energy that it can absorb. So it goes in there, and there's a certain amount that this is able to accept. The electrons go to a certain, let me get this out of the way. That would help. A certain amount of energy that it can accept. And then when it emits it, it would actually be less energy, right? So that would be, if it's emitting less energy than it takes in, would that be a higher frequency or lower frequency than what went in? High frequency went in. Lower frequency. Okay, high energy. And then as it emits, you get a lower energy coming out. So it's constantly going up and down. That's what is making it glow. Okay, because we're constantly putting energy in there. And if we stop the energy, of course, this goes away. The moment I turn it back, the moment I turn it back on, it actually is on. It just takes a long time to get going. But anyway, you get the idea. So that's something you're going to have to explain in your paper, right? You're going to have to look at the emissions that we can accept photons that say high energy photon. It goes way up in energy from up to a high level shell, could even kick them off. And then it goes down to lower level shells, each time emitting a photon. But the photon has less energy when it goes down because it's a shorter distance. You can stick a whole bunch in, but then it goes so much, and then there'd be some left over, which would then be would fly off as a different color. And so this is actually glowing. That is actually emitting light.
Since instantaneous travel is possible at a quantum level, is the energy transfer between a photon and an electron 100% efficient?
It should be.
Should be.
Approximately. It gets into more detailed physics at that point.
Then why does it emit a lower frequency if energy transfer is 100%?
Well, we'll just say it's 100% efficient. It has to do with why a line spectrum is not exactly a line. because there's some quantum smearing
Oh boy.
of light interfering with itself. So, yeah, something you don't want to get into very much. So as far as we're concerned, it's just emitting exactly that amount. Because Bohr said so, and Bohr happened to be pretty much right. Okay, that's what he discovered. So it was an observation. It was a law. You can say there's a quantum law that it absorbs and emits a particular frequency, and only those frequencies. And when we don't have the black light, when we're not supplying constant energy source, it doesn't do that. Okay, does everybody have enough information for their little write-up?
Do you want them 2 and 1, both in the same lab, or do you
In
want
the
two?
same lab,
Okay.
because we're talking about light, so we're talking about emission.